first speaker is Professor Yang from National Chiao Tung University, next to National Tsinghua University. He is going to tell us about universal behavior of the speed of sound in QCD from holography. Please start.
So very happy to have this chance to present our recent work about the speed of sound in QCD and from the holography. And in this morning session, some speakers already introduced the idea of the holography. And roughly speaking, it just tells gravity theory and field theory is equivalent to each other. So we can study the gravity theory to get some properties in the field theory. And this particular topic is the field theory is QCD. So we want to understand some properties in QCD, and we want to study gravity theory which corresponding to this QCD. But of course, we don't know exactly what's the gravity theory which corresponding to QCD. So we study a general class of gravity theory which at least can produce some major properties in QCD, such like Meson spectrum, phase diagram, or like equation of state, and so on. Okay, and in this talk, we will study the speed of sound in QCD. So roughly speaking, the theory I study is the gravity theory. So I will study gravity theory and use the gravity theory to get some information in the QCD theory. Okay, so after a brief introduction of speed of sound, I will give a description how the speed of sound looks like in QCD, and here is in the holographic QCD. And we will explain and how to use this model to get some universal behavior of the speed of sound in QCD. Okay, so I think everybody knows what the speed of sound. It's just so every day we speak, so you can hear me. Sound is appropriate to your ears, so you can hear me. And the speed of sound is quite slow compared to the speed of light, right? So in the air, in the left probably it's just a speed of sound in the air. So it's about 300 meters per second. And in the right is speed of sound in the water. So it's a little bit higher. It's about 1.5 kilometer per second, but it's still pretty low. And we can see that from this diagram. The speed of sound is dependent on the temperature. So if you change the temperature, the sound will change because this speed of sound have to be propagated in the medium, and the medium depends on the density and whatever many properties of the medium. So if you change the temperature, the medium will be changed. So the speed of sound also will change. So what I want to see is in the QCD, we know there's many different phases in QCD. Like in the low temperature, we have the baron phases, and in the high temperature, we have the quark phases, and the medium has some quark-gluon plasma. So you can imagine that the speed of sound in QCD should get a little bit complicated than this just in the water or in the air. So it looks like this, but this one is not the experiment state. So unfortunately, we don't have experiment state for speed of sound in QCD. And this one is coming from the lattice QCD. So basically, we treat this lattice QCD result as the experiment state. We don't have a real experiment. So this is from the lattice QCD. And we know that lattice QCD, for some reason, is only it works well at zero Kemp potential. That's basically zero. So we have this typical profile of this speed of sound. Versus is the temperature in the MUV. So let's see what's some properties of this speed of sound. The first one is there is a minimum point. It's around TC equal to 150 MUV. And this is the so-called the softness in the equation state in QCD. And this pattern is around the phase transition point. And this phase transition is dependent from the deconfinement phase to the confinement phase. So it's around here. And from lattice QCD, at least as a nu to zero, this one is not a real phase transition, it's some crossover. We still have the minimum point, but it's kind of crossover. So it's a smooth function. It's And that's the first feature. And the second one in the high temperature limit in this way. And we know that the QCD in the high temperature limit goes to the free ground gas. So it basically is kind of massless ideal gas. So for massless ideal gas, it's already calculated that the speed of sound should be approached to the conformal limits 1/3. So we can see this calculation, it does goes to the 1/3. So this one is the conformal limit, and it goes to the 1/3 in the high limit. So that's the second property of this speed of sound in QCD. And in the low temperature, well, here we don't put very low, but we know that in the low temperature it goes some value. But so far we don't quite know what the value is, but for the electric QCD cannot go that far. So that's the result from electric QCD. And another most important thing is if you look at this one, that one, you will see that whatever there is a limit. The upper bound for the speed sound is 1/√3. So, and that happens at high temperature limit, and any other temperature is below that. But there's no much reason to explain that. We know that the only thing you can say that is the speed of sound should be less than the speed of light. And here we treat that as equal to 1, so it should be less than 1. But here is the electric result tells us it should be less than 1/√3. So we don't really understand what that means. So that's the question from here. Okay. So next, let's see from the holography. We're trying to use some model from string theory to build a gravity theory, and those gravity theory describe this QCD. And initially, we don't have the QCD. We have some other field theory, like early time, 2002. People has studied the theory, and it has 5 times as 5 is corresponding to the 8-4 Pelmel theory. And because this theory is the conformal theory, so exactly the speed of sound is the conformal limit. That's 1/3. So that's can be calculated. And of course, we want to break some supersymmetry to do something more similar to the real QCD. So if you break some supersymmetry, you can go to N/1 Pelmel theory, and that's corresponding to in the graphic side, corresponding to the Kurbanoff-Dressler background. And that's in the 2005, some people have calculated that speed of sound in this background. And we found that the speed of sound equal to the 1/3 minus something. And this calculation is in the high temperature limit. Because the background is so complicated, you cannot do formulas, the 4 formulas. You can, in the high temperature limits, you can get this one. So we know that in the high temperature limits, it's roughly goes to 1/3, and it's from below. That means it's less than 1/3. It cannot be beyond that, because this one is positive and here is negative. But of course, there are some other higher order fractions. But from here, we can say that it should be approach the 1/3 from below. And that's from some top-down model. And top-down model is good, because that's from exactly string theory. But the bad thing is the corresponding field theory is not really like QCD. So another way is bottom-up. And the bottom-up model, we don't directly from string theory, we just put the gravity theory by hand. And to make the corresponding field theory looks like QCD. So, okay, so here is a well-studied model of the bottom-up, and basically the software model. So it's coupled to the gravity with the scalar, with the scalar potential like that. If you study this one, and in 2009, some people studied this so-called Einstein scalar system, and they also found in the high temperature limits, this speed of sound can be expressed in this way. So it's also the 1/3 minus some positive things. So that means it's when in the high temperature, this speed of sound is approach to the 1/3 conformal limit and from below. So it's always less than 1/3. That's the only for the high temperature limits. But until that time, all of the models, they calculate the speed of sound. All of them, there's no example to show the speed of sound can be beyond 1 cell. So the author of these two papers just conjectured that for an arbitrary temperature, this should be held. That is the extreme upper bound for the speed of sound in QCD. Okay, so here is Gupser has a very nice paper. That's the first time used the holographic QCD to give the whole picture of this speed of sound through the whole temperature. But this one is a numerical result, so you don't have that nice explanation. So let's see this one. Let's compare to the right one is from the bright color, it is from the gravity background, and the blue one and the purple one is from lattice one. So that's the compare the lattice base to the bright. So compared to these two, we have the crossover FTC. So that's a good thing. We know that there's as a phase transition part. So here's a POT for 1. There should be a crossover. And also in the high temperature limit, this goes to the 1/3. And there is another actional feature from this work is because their background is not really has much physical meaning. They have some parameters which don't know what's the physical meaning. So they got this one. They got this diagram. It's just judged this parameters, and happily they can be this one. If you change the parameters, they change to some other curve. So they just address this parameter to get this one to fit this lattice state. And they found that if you change the parameter to some other part, you will find this one is you can change this crossover to a second order transformation. Once this second order transformation happens, this speed of sound will go down to the 0, then go up again. So that means at this critical temperature, because at the second order we have a critical temperature, at this critical temperature this goes to 0. So that's perfectly studied in this paper. And but all of study is for the neutral 0. That's 0 can continue. So if you look at the QCD phase diagram, you know that if you including the chemical potential, the phase is really complicated. So for the 0 chemical potential, we know that there is a phase transition at some crossover at some temperature. But if you increase the chemical potential, you will say at some point, this part, this critical part, we do have a second order phase transition. And beyond that, we have a first order phase transition. And if you keep increasing your chemical potential, you'll find that this guy give another new phase. We call it the colors of the conductor, because we have a very dense measure here. So we have the colors of the conductor. So if you want to, so our work is just really trying to study the speed of sound in terms of the finite chemical potential, and to see what we put on. So that's what we want to do. Okay, so let's introduce our background. So the background is if you want to study the chemical potential, including chemical potential, you have to add another Maxwell field. Now this is due to the AGS-DLT, so I don't want to explain too much. And we want to, so that means the background we study is Einstein-Maxwell scale system. In terms of this, instead of this one, in addition to this one, we have one more Maxwell field. And we want to study the general dimension, is d equals 2. So when d equals 3, it goes back to the normal 3 plus 1 QCD. So that's our start point. And we want to solve that, we should give some answers. So we have 3 fields. So metric we have this, we need some bugs, asymptotic ADS, black hole. So it's, the answer is look like that. And for the Maxwell field, we give this gauge potential A equal to AT. That means only the T component of A has the non-vanished and all the other is point. Only this one corresponding to the tangent potential, and the others correspond to some other like electric field, external electric field. We don't want to count those things. And also this phi, and phi, the unsatisfied is also quite zero. So next we plug in all these things to the equation motion, and we got this. So that's the motion for our phi, ATW, and we have one more is for some constraint. That's coming from the Einstein equation, and also the equation motion from the gauge field and the scalar field. So basically, this system is also been studied by many authors. But if you look at that, the first idea is using numerical, right? So almost all the people use numerical. And we just find a way to get an analytic solution of this one. So that's why we can use this analytic solution to analytically solve the field sum. To look at more property of that. If you just look at the numerical, you don't have the good control of this function. So yeah, I don't want to give you the details how to solve that. I just present the solutions. So the solution is like that. The scalar is very simple. It's just equal to this one, and W is a back vector. It's the arbitrary function, and the only basically W can be any function, but it should obey some conditions that W prime square should be larger than the double prime, because we want this scalar field to be real. So that's the only condition we need to let this W. That is fine. And also the gauge field is like that. So the gauge field in the expansion, sigma 0 should be give you the cap potential and also the density. So that's the ADS detection. And also the last, the most important is the metric. The metric is a little bit complicated, something like that. And we're inside I1, I2, there's some integral. So it's an integral only depending on this W and the dimension. So I can say that at mu to 0, this G is very simple. But if you include in the cap potential, it's going to be a so that's the analytic solution. If we have the boundary solution, it's a background, then we can start to calculate some of the dynamic quantities, like its temperature. It's just the Hawking temperature. So you can, if you have the background, radical background, it's just this formula to calculate that. So the temperature can be written down in this way. And where the T0 is just the temperature at the 0 cap potential, and T0 equal to that. So from here, we can see that the T always less than T0. So that's the important feature we'll use later. So the T0 is larger than T. And for the entropy, it's simple. It's just the surface of the horizon. So that's it's a simple function of that. And the baryon density can be written down in terms of temp potential like that. So if we have all of the things, you can carry this cube sum. Use these thermodynamic formulas to calculate. Just plug in everything in here and calculate that. And from here, we can say that is it around the critical temperature, this S and the rho has the maximum changing rate. So that makes this a cube sum. It has the low minimum point at critical temperature. Okay, so if you plug in everything into this formula, you got a little bit of long calculation, and just sit down and calculate. And after all, you can combine everything to a very compact formula. And this formula is not this formula is for arbitrary temperature and temp potential. So that's a complete analytic formula for the sleep sum usually. So if we have that formula, we can do some analysis to see what behavior of this formula is, because we can have full control of this formula. Okay, so let's see what's inside these parameters. So for CS0 square is just the sleep sum at the 0 temp potential. So that's totally simple function. And this CS0 future square is just a constant, E minus 1, 65. So we'll see later what is meaning of that. And we have two other parameters. One is A, is the function of the density, temperature, and blah, 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 something like that. And also another function is B. It's also depend on this potential density something. And we can, it's easy to say that from these two formula, both A and B are positive. See, but the square and the temperature have to be positive, and this is E. Exponential is positive, and everything is positive. So everything is positive. So that's from this result. Then we can do some analysis for this behavior of the skip sum. So first, let's look at the skip sum that's equal to 0. So that's a simple thing. We tend the left equal to 0. So we calculate this 0 skip sum when t infinity. So to calculate that, we just calculate this limits, and you plug in everything into the fund. This one doesn't depend on what the W is. We said that for the background, the W is the arbitrary function, almost an arbitrary function, only sense of a condition. But this one doesn't depend on this W. This one exactly gives the 1 over D. If you plug everything in, and because T0 also depends on W. So yeah, plug everything together, and this goes 1 over D. And of course, in the 3 dimension, that's goes to 1 over 3. So we can easily prove that at 0 cap potential, this high temperature limit is equal to 1 over D. And for the high temperature expansion, we want to do something like the other people did before. So we do this expansion, and we found out that's equal to the 1 over D plus some correction terms. And these correction terms, and here is depend on the dimension, of course, it's positive. And here, that's the important thing. This guy is negative, right? We already said that to make sure the scalar field to be real, this one should be greater than that one. So that means this guy is negative. So if this guy is negative, that means this contribution is negative. That means this guy is at 0 cap potential, this skip sum is less than 1. So that's exactly the same result as before, but it's easier to see from this model. Okay, so that's this from the high temperature. So we want to prove that at arbitrary temperature, this guy is less than the 1 over D. So we can just, because right now we have the full formula, so we can really do that. We can try to do this derivative to see at where this skip sum has a maximum point. And you just solve this guy to 0. And if you solve that, and the solution is just CS squared to that one. That's the point as a maximum value of this skip sum. And same thing we use is W double prime should be greater than W prime squared. You know that this guy has a point. So this proof is for actual temperature. So that's gives us for this, at least for this kind of background. And the skip sum at 0 cap potential always less than 1/3, and approaching to the 1/3 at high temperature. So next, we want to go to possible finite cap potential. For finite cap potential, the first thing we want to see that also we want to take the high temperature limit to see what happens. And for this A, do that. And it's easy to say that for high temperature limits, this guy gets 0. Okay. And the full skip sum is actually look like that. And if A equals 0, it just simplifies to skip sum at 0 cap potential. So if you take the limits, of course, it's 1 over D. So that means at finite cap potential, its skip sum also approach to the 1 over D high temperature limits. And next, we want to prove that for the arbitrary temperature, go down here. So at arbitrary temperature, we use another feature is that T always less than T0. That's it. So if T always less than T0 and B is positive, so we know that the whole thing, this guy should be less than this guy. And this guy should be less than the maximum value of the CF0 of C2. So we can easily prove that. So we already proved that this guy is less than 1 over D. That's the 0 cap potential skip sum. It's always less than 1 over D. So this guy is constant. So this is just constant. So yeah, so So if this one, if you want this one less than 1 over t, this t have to be less than or equal to 7. So that means we can prove at least 1t less than 7 as the dimension. Yeah. We can prove this slip sum less than 1 over t, yeah, for arbitrary temperature. Okay, so for mu to infinity, so we see for mu to infinity, some people conjecture that it should be also go to the conformal limit one third when this mu goes to infinity. But we calculate that some different result. Let's see. So if we want to calculate the mu go to infinity, we look at our formula for temperature, and this temperature equal to T0 minus this one. And there's of course there's a problem that when mu go to infinity, this temperature goes to negative, and that's not really good. So we don't want temperature goes to negative. We want to have a fixed temperature. Right? We want to make the capital potential go to infinity and the temperature fixed. So that means if we want to make mu go to infinity and temperature fixed, we also should be let the ZH go to 0 together. When ZH goes to 0, this one also goes to 0. So if you make these two, we call the double limits. If you take the double limit, then you can take the T fixed and the temperature potential go to infinity. So in this double limit, we also can look at this parameter A, this function A, with its behavior. So the function A is just like that. And the double limit, when mu goes to infinity and ZH goes to 0, you can see that because T is constant right now, and all the others is some well-behaved function, but rho will be go to infinity, because we remember that rho just proportional to mu. We solve with mu. So that's this guy will go to the infinity at this double limit. If this goes to infinity, we can see this slip sum under this double limit is this one under this double limit. Because A goes to infinity, so we can ignore this term and cancel all the terms and only this one left. Okay. So what we have is under this double limit, we have 1 minus t, t0 minus t, and c2 term here. So here we have, because this one is constant, so this limit only takes t, t0 minus t. And here I didn't show the details. If you plug in the t and t0, we will have the formula just here, actually, here. And that's the function of th. If let th go to infinity and the mu goes to infinity, you found out it's nothing, just one would be this limit. So that means this guy equal to c tutor over d. So that's the d minus 1, 16 pi d. So that's a constant. So we just so here we just prove that as fixed temperature and infinity temperature potential, and this slip sum goes to a constant. But this constant is not 1/3; it's another constant, so another universal constant. It doesn't depend on the background. It's only depend on the potential. So, and this one also implies that at the very high temperature potential, we should have a new phase comes out. And this new phase has this slip sum that's different from the conformal phase. And so that's the consistent with conjecture that in the very large temperature potential, we have some colors that's different from the normal city. Okay, so the last limits we want to discuss is some t to 0. Initially, nobody really need to take care of that. I think I remember only 1 or 2 papers we really study this t to 0 limit, but we use extension. But here we can just do this limit and to take calculation. So when t equals 0 and similar this a equal that. When t equals 0, that's totally fair. That's also easy to see. And if you plug in this a go to infinity to this formula, you also left this guy. But when t equals 0, that means here is 0. T equals 0, t0 also goes to 0. This was the same thing. So that goes to 0. So this guy is nothing, just the c tutor. That's 0. So So that's its constant, d minus 1, 6 pi. So we know that what is the parameter, the physical meaning of this parameter? It's just the speed of sound at the 0 temperature. C tilde at 0 square is just the speed of sound at the 0 temperature. So that's another universal constant. It's only dependent on the dimension of this dimension of the zero rating. So almost done. So that's so far we consider 4 different limits, and for each limit we got 3 different universal constant. Right. So 1D and this guy and we got a large temperature. And also prove that everything is below the 1/d for actual temperature. So that's some work by formula. Let's look at the plot. So if we really pick up a concrete model, to look at what the plot is. Now here we just pick up a model that we calculate this year. Actually, for this model, we just really want to calculate the phase transition of the QCD. But we just pick that parameter in that model to plug in this formula to see what the sound looks like. So the split sound for the different potential look like that. So the behavior is just what we see. That at high temperature, it goes to 1/3. And at the low temperature, it goes to the 1/8 pi, and that's for D equals 3. And that's also for different potential equal to the same value. And this part is critical temperature with the largest one. You can see that it's still not enough, right? So for this proper one is closed over. You can see that go here and can zap. And for the critical part, we have the critical part. For the critical part, it's D goes down to here, it's a blue one, and going by. So for the critical part, where is the phase transition in second order. So the speed of sound goes to 0 and then going back. And for the larger potential, you can see that this slide goes here and then turn around and going back. So at this part, they have some phase transition as a first order phase transition. So it's also look at that. But at this part, it's not continuous function. So that's speed of sound. Versus the temperature. And also you want to keep the temperature, we want to look at what is speed of sound versus the temperature. So that's perfect now. And that's for the different temperature. And this one is the low temperature, and here is the high temperature. And this part is just the effect of this small slash. And you can see that for the large potential, everything just goes to a constant. And this constant is 1/24 pi. Which is just equals 3 without the large potential the value of that. Okay, so that's a summary. The summary is a mirror dot over this study is that we really calculate, we have the model and calculate the speed of sound and give the full analytic formula for this CS and prove that for any temperature is less than 1/d. So in 3 dimensions, that's in 1%. And we found 3 different universal value. For the t equals to infinity, that's give the conformal value 1/d, and in 3 dimensions, 1 to 3. And if t equals to 0, we have another value as d minus 1/16 pi, and in 3 dimensions, it's 1/8 pi. So it's already showing the diagram. And also in the large time potential, this S curve goes to this another new constant. And in the 3 dimensions, it's 1/24 pi. It's finite. So that's what I want to discuss.
Any questions or comments?
So, what property is important to ensure these inequalities? So Einstein equations or?
Yeah, actually it's a solution. It's a background solution. That means this proves that the Einstein scalar Maxwell background always has this property.
So I'm wondering that if you include the higher derivative corrections to the Einstein gravity, so this bound is broken.
Yeah, if
Like in
you,
the
yeah,
example.
yeah, yeah, of course. If you modify the Einstein gravity, then this one is not guaranteed. Yeah, and also there's some people that if you include in some like isospin cap potential, is also not guaranteed.
Any other question? Okay, so then let's thank the speaker again.